Hi there and welcome back to the College Physics series. In today's lesson, we're going to be talking about an intriguing idea that is relative velocity. We are going to explore why an object's speed can appear to look differently depending on how you observe it. Be sure to download the guided notes in the description so that way you can follow along throughout this lesson. Thank you for being here. Let's get started. Imagine you're riding in a car at a high speed and you see another car moving alongside you. Strangely, that car might look like it's barely moving. But if you were standing still on the sidewalk, that same car would seem to zoom by. So what's going on here? Today, we're going to break down why the same motion can appear to be different, all thanks to the idea of relative velocity. Let's take another example. Imagine you're watching a friend running by. To you, standing still, they're moving forward pretty fast. But if someone else were running alongside them at the same speed, they'd see your friend as if they're barely moving. And if someone were driving faster than both of them, your friend might even look like they're moving backward. In today's lesson, we're going to explore this idea of relative velocity, the idea that the speed of an object depends on the observer's perspective, or what is called their frame of reference. This is a critical idea because, as we'll see, there is not a single quote-unquote true speed for the runner. Each perspective is valid depending on the observer's motion. To understand this better, let's look at a scenario involving three friends, Amy, Bill, and Carlos, who are all watching a runner. Each of them is observing the runner from a different position. Amy is standing still, watching the runner move forward. So, from her perspective, the runner appears to be moving forward at 5 meters per second. Bill is riding a bike, moving alongside the runner at exactly the same speed. Because Bill is moving along with the runner, he sees the runner's legs moving up and down, but as far as he's concerned, the runner isn't going forward or backward at all. To Bill, the runner's speed is 0 meters per second. So if Amy is stationary, her speed is 0, and she sees the runner moving at 5. If Bill is going at the same speed as the runner, he's also moving at a rate of 5 meters per second. But what Bill observes is that the runner's speed is 0, which we will get to in just a moment. Carlos is in a car driving faster than both the runner and Bill. He sees the runner moving away from him in the opposite direction, appearing in his rearview mirror at -10 meters per second. In yellow, I've written what each observer claims the runner's velocity to be. So Amy says, I see 5 meters per second. Bill says, I see 0 meters per second. And Carlos says, I see -10 meters per second. But what I have written in white are the speeds of each object according to Amy, since Amy is at rest. And these pieces of information are going to be important in just a few minutes. So if Carlos sees the runner moving backward at a rate of -10 meters per second, how fast is he actually going? What this -10 meters per second means is that the distance between the runner and Carlos is growing. And from the set of eyes from Carlos, he sees the runner moving backwards. This means that Carlos is moving at a rate of 15 meters per second because the difference between their speeds is 10 meters per second. That is the rate at which they are separating. From the runner's perspective, Carlos is moving towards the right. He's getting farther and farther away at a rate of 10 meters per second. Why? Because he's going 10 meters per second faster. But to Carlos, it appears as though the runner is moving towards the left, hence the negative sign at a rate of 10 meters per second. It's important to understand this nuance. So here is the big question. Who is correct? What is the runner's true speed? What we are seeing here is a concept in physics called relative velocity. Relative velocity tells us that the speed of an object isn't absolute. It depends on who's observing it. In this case, each person, Amy, Bill, and Carlos, has a different view of the runner's speed, and each view is correct for that person's frame of reference. In physics, we can describe these different views with something called relative velocity notation. This notation allows us to specify the object's speed and specify who is observing it. For example, we write the runner's speed relative to Amy as the horizontal velocity in parentheses, and then we're going to include subscripts in the order of r and a, and that is 5 meters per second. Here, the subscript RA means runner relative to Amy. That is what the R and the A means in that order. R is for runner relative to Amy. Altogether, we read it as the horizontal velocity of the runner relative to Amy. Bill, who's moving alongside the runner, would say the runner is moving at 0 meters per second relative to him. So we write this as VXRB. This reads the horizontal velocity of the runner relative to Bill. And he claims the runner is moving at 0 meters per second. Lastly, Carlos, driving faster, would say the runner is moving at negative 10 meters per second relative to him, which we can write as VXRC equals to negative 10 meters per second. This tells us that there's no single absolute speed for the runner. Each of these speeds is quote-unquote true in the context of the person observing the runner's motion. Now that we understand each observer's view of the runner's speed, let's calculate the runner's speed from Carlos's point of view using what we call the relative velocity formula. Here's the situation. We know the runner's velocity relative to Amy, and we know Carlos's velocity relative to Amy. We'll use these to calculate the runner's velocity from Carlos's perspective. First, let's understand what it means to say Carlos's velocity relative to Amy is 15 meters per second. Since Amy is standing still, she's considered stationary, and Carlos's speed is 15 meters per second faster than Amy. This means that if Amy were watching Carlos, she'd see him moving away from her at 15 meters per second. We write this as VXCA equals to 15 meters per second, and this represents the horizontal velocity of Carlos relative to Amy. Remember the order that we use for these subscripts. The C comes first and the A because it's Carlos relative to Amy. To calculate the runner's speed from Carlos's point of view, we're going to use this formula. VXRC equals VXRA plus VXAC. Let's break this down. VXRA is the runner's velocity relative to Amy. VXAC represents Amy's velocity relative to Carlos. Since Carlos is moving faster, Amy appears to be moving backward to him at negative 15 meters per second. So we write VXAC equals to negative 15 meters per second. Here's why we use negative 15 meters per second. If Carlos thinks of himself as stationary, let's refer back to this picture. If Carlos thinks of himself as stationary, he'd see Amy moving backward at 15 meters per second. So we assign a negative sign to reflect this opposite direction. The formula works by aligning the frames of reference. Notice that the A term appears in both RA and AC. By using these common terms, we can remove Amy's frame of reference and find the runner's velocity directly relative to Carlos. In this sense, the formula works like a chain, connecting the runner's motion to Carlos's frame through Amy. Another way you can think about this is that the terms in the center, in the middle, cancel each other out. And what's left over is R and a C. And that matches with the RC that we're looking for. So the ones that you're looking for are on the outsides. And in order for the inner terms to cancel, they must be the same. Another quick note is for us to pay attention to this value and this one. Notice that the only difference is that the subscripts are switched. Here I have CA, here I have AC. And notice what that does. It flips the sign. So there's a relationship that you should be aware of where VX AC is going to be equal to negative VXCA. When you flip the scripts, you're also going to negate it. Now let's plug in our values. VXRA, the velocity of the runner relative to Amy, is 5 meters per second. Plus the velocity of Amy relative to Carlos is negative 15 meters per second. Therefore, the velocity of the runner relative to Carlos is negative 10 meters per second. So Carlos sees the runner moving away at negative 10 meters per second. This negative sign simply shows us that Carlos observes the runner going in the opposite direction relative to him. Let's try an example. This example reads, imagine an athlete throwing a javelin while running forward. The athlete's speed relative to the ground is 6 meters per second. The javelin speed relative to the runner is 15 meters per second. What is the javelin speed relative to an observer standing still on the ground? Let's quickly picture this. So we have an athlete moving, and he's carrying this javelin with him, and the runner is moving at a rate of 6 meters per second. What happens is that this runner throws the javelin. So it's flying through the air, and the runner sees this javelin moving at a rate of 15 meters per second. What we want to know is what a random audience member would describe the speed of the javelin as. What the question is asking for is, how would a random observer standing still on the outside describe the speed of that javelin? Let's write down what we know. We know the athlete's speed relative to the ground is 6. I can write that like this. The horizontal velocity of the runner relative to the ground is 6 meters per second. The javelin speed relative to the runner is 15 meters per second. And here's how I'm going to write that. So this is the speed of the javelin relative to the runner, and that's 15 meters per second. What we are looking for is the speed of the javelin relative to the ground, because that's what any observer would see. In order to figure out that speed of the javelin relative to the ground, we need to set up the relative velocity formula correctly. I know that if I want to find the speed of the javelin with respect to the ground, those subscripts need to be in a certain spot on the outside. And I know that the inner two subscripts need to match. So the J stands for the javelin, the G stands for the ground. The only other third object involved in here is the runner. So what this would represent is the javelin's speed relative to the runner. Do I know that? Yes, I do. The RG would represent the speed of the runner relative to the ground. That I also do know. Because the R's are toward the inside, they're going to cancel out, and I've properly set up my relative velocity formula. Therefore, I can plug in the speeds that I know. VXJR is 15 meters per second. Plus VXRG is 6 meters per second. Therefore, an observer on the outside would observe the javelin moving at a rate of 21 meters per second. Let's do another example that's slightly more challenging. Our next example reads, a boat is sailing directly north across a river that's 300 miles wide. The boat's speed in still water is 500 miles per hour. The captain is unaware that there is a current flowing east at 100 miles per hour. What is the boat's velocity relative to the ground? Before we do any calculations, let us first draw a picture. Here is my river. It is 300 miles wide. Here I have my boat. And in still water, I know that this boat can travel at a rate of 500 miles per hour. What the captain is unaware of is a current moving towards the east that is 100 miles per hour. Notice that in this example, my velocities have direction. So I'm going to need to take that into account. What I know about my boat is this. The velocity of my boat with respect to the water, to still water, is 500 miles per hour, directed towards the north. I know that the velocity of the water with respect to the ground is equal to 100 miles per hour towards the east. The question is asking me, what is the boat's velocity relative to the ground? I'm looking for the velocity of the boat with respect to the ground. And that just means if someone is standing on the shore, what velocity are they going to be observing? Now, for me to set this up correctly, I need the inner subscripts to cancel. Because I'm looking for VBG, the velocity of the boat with respect to the ground, here I'm going to have a V, it's going to start with a B, and then I'm adding another velocity, and it's going to end with a G. The only other subscript that matches in this scenario is the water. So I need to know the velocity of the boat with respect to the water, which I do, and the velocity of the water with respect to the ground, and that I do know. Therefore, I've set up my relative velocity formula correctly. What becomes slightly more complicated about this problem is the fact that I'm dealing with vector quantities. So I need to add up these vectors, including the magnitude and direction. So my final answer is going to take this form. The velocity of the boat with respect to the ground is going to have a magnitude and a direction. Let's draw out the scenario. I know that the velocity of the water with respect to the ground is 100 miles per hour directed towards the east, so this arrow is drawn towards the right. I also know that the velocity of the boat is directed towards the north at 500 miles per hour. The resultant, or the sum of these two vectors, is going to represent the magnitude of the velocity of the boat with respect to the ground. And the angle is going to be my direction. So all I need to do is the Pythagorean theorem to figure out the hypotenuse, the resultant, and then use a trig function in order to describe the direction. And then my problem will be complete. To find the magnitude, I'm going to use the Pythagorean theorem. Simplifying this out, I'm going to get 510 miles per hour. And that completes half of the problem. So here I'm going to write 510 miles per hour. Next is the direction. This angle theta is measured from due east. So here I'm going to do the inverse tangent. The direction in which this boat moves is measured from the east direction. So opposite to this angle will be 500 and adjacent will be 100. Therefore, I can use the inverse tangent, which is just opposite over adjacent. And that's going to be 500 miles per hour over 100 miles per hour. In physics, what you should find is that the input to a trig function is dimensionless. You should always get that. If you do not, please recheck your work. So what I'm going to get is the inverse tangent of 5 over 1, which is just the same thing as 5. And that's going to be around 79 degrees. Now, which direction is this in? So we started heading east, and then we headed up towards the north. So the way we correctly describe that is north of east. Remember, the second direction is where you begin, and then the first direction is where you're headed. So the final answer for this problem is that the velocity of the boat with respect to the ground is 510 miles per hour at a direction of 79 degrees north of east. To sum up, relative velocity helps us understand that there's no single true speed for an object. Each observer has their own valid measurement depending on their perspective. This idea applies to cars, planes, runners, and even objects in space. If you found this video helpful, go ahead and give it a like, and consider subscribing to the channel. Thank you for being a part of the College Physics series. I look forward to seeing you in the next lesson.